Hi there, in this video we're going to look and see what happens to a function in the frequency domain whenever we integrate it in the time domain. Okay, so the previous video was about differentiation and this one's about integration. So the idea that we're going to work through is that we can integrate a function by taking the function, say f of t, this is the function we wish to integrate, and if we convolve it with a unit step u of t, then we will find the integral of that function f of t. Okay, so that's the idea. Now we can describe that graphically. So we know that if we're going to do convolution, we take one of these and we flip it in the one of the axes. Okay, so let's take the step function and we'll do the flipping on the step function. So I'll just draw this out along this line here, just to get as a reminder. Okay, so the step function there, we'll just write that as u of t. Okay, so u of t is 1 when t is greater than or equal to 0. Okay, and it's 0 when t is less than 0. Okay, now the idea of convolution is that we introduce a dummy variable. Okay, so we just introduce that dummy variable here. Okay, so we'll just rename that u of tau, so tau is the dummy variable, and then we will mirror it in this axis, so then we end up with a function that looks like that. Okay, so that will be u of minus tau, and then what we'll do is we'll take that function and we'll shift it along this axis. Okay, so we're going to be adding on some factor, we can call that factor t. So we could end up with, as an example, the function might end up there, so we call that t1. Okay, so this function here would then be u of, and it would be minus tau plus t. Okay, but we don't write it as minus tau plus t, we just write it as t minus tau. So you just end up with a function there is u of t minus tau. Now what we're going to do is, if I draw it in a big axis there, we're going to take this function now of, replace the variable f of t with f of tau. Okay, so that's f of tau, and we have this other function u of t minus tau, and I'll just draw it in this axis here. Okay, so that's our u of t minus tau, and this comes in and it's moving in that direction. So now we will form the function f of tau times u of t minus tau, right? So that's the start of the convolution. Now we know from looking at this here graphically that if we call that point t, so that's the addition of some increment, so we'll call that point there t, and if we call this point here tau, then we know that this product here is going to be 0 whenever our value of t is less than tau, because there's no overlap. This function here has not started to overlap that function yet, so we'll say that equals 0 for values of t less than tau, and we know that it's going to equal, well, we know that's height 1. Now this function could be any function, it could be any height, so whenever we shift this over the top of this, then we're just going to have this u of t minus tau, it will just have a value of a height of 1, and the function f of tau will have some value f of tau, so the final product here will just be 1 times f of tau. So we'll have it equaling f of tau whenever our t is greater than tau. Okay, so when t heads in here and it passes the tau, the value tau will actually get an overlap. So if we were to continue and actually look at this, overlapping. So there's our f of t. When this comes in here, let's say we pick one point there for the overlap, and we'll draw the convolved function below. So there's nothing happening here, and then at that point there, all of a sudden there's a small increment in area. Okay, so we'll take a point there, so that area there will be this height here. Now when it shifts along to the next one, then the next height will be the combined areas. Okay, now the time difference here is the same. Okay, so the time step's the same, so the movement over here is the same, so the height there is going to get doubled, so that height is just going to get doubled for there. Okay, and again if you move up to the next one, you've got the combined area, so it will be 3 times, 4 times, 5 times, so that just follows a linear path like that. Okay, so in effect what's happened there is that shifts across. This function here has been integrated. Okay, and you can see that as well if you work back the way. If you think about this here, we can say whenever we differentiate this, we get this here, and you can see that because it's just a gradient, so it's a fixed gradient, so it means that this height here is just this fixed gradient. Okay, so you can see that that there has actually produced an integral, but if we were to then write the full convolution out, then the full convolution would be integral from minus infinity to infinity, and it would be f of tau u of t minus tau. Now if I let this run off over here to infinity, it will just keep running. This point here will get to this point here, which is here. The integration would have been done, but when we let it run over, it will keep running that way. Okay, and this goes off to infinity, minus infinity that way, so there will always be an overlap here, so that will just increase and increase off to infinity. Okay, as we go past this point. Now we don't want it to do that, we just want to get to that point there and say, well, that's us done our integration, we'll go back down to 0 and we'll continue along like this. Okay, so what we want to do is we want to limit the upper limit of this integration, so we want to be able to integrate from minus infinity to some value. Now the value we'll call t, and t is the upper limit of this function here that we want to integrate. Okay, so it means that we can rewrite this out, and we can say that if we do that, f of tau u of t minus tau, this here will just be equivalent to finding the integral of our function, which is, we'll just call it back to t integral, so the integral from minus infinity to some value t of f of t by dt just equals our function f of t convolved with u of t. Okay, so that's a little graphical proof that we can integrate a function by convolving it with a unit step, okay, in the time domain. Now we've already gone over and we've seen that we can write this unit step, and there's a video there on the unit step, okay, which shows it all in MATLAB. Okay, so we can Fourier transform this u of t, and when we Fourier transform u of t, what we get is we get a 1 upon j omega plus pi times delta omega. Now what we're saying is that if we take a function in the time domain and we convolve it with a unit step, well, convolving two functions in the time domain is equivalent to multiplying them in the frequency domain. Now we proved that in the previous video, so really what we can say is we could say our g of j omega, okay, which is our integrated function, is going to equal u of j omega, which is a unit step, times f of j omega, which is the function that we wish to integrate. Okay, so it means that we can then rewrite that there as, well, our u of j omega is the Fourier transform of u of t, which is this here, and then we're multiplying it by f of j omega. So the final thing that we're going to have is 1 upon j omega times f of j omega plus our pi delta omega times our, space in here, times our f of j omega, f of j omega. I just squeezed that in there. Okay, I'll rewrite it down here anyway. Okay, so this here is our Fourier transform, so of our integrated function. Okay, so we can then write the transform pair, and I'll just write it down here, the integral from minus infinity to t. I'll just use the f of t by dt, and the Fourier I'll bring that down a wee bit. I've not got enough space there to squeeze it in like that. So we know the Fourier transform of that. Okay, so the Fourier transform of that is just this one thing here. So it's 1 upon j omega times the f of j omega plus, now another little extra thing here is we'll have our pi of delta omega. Okay, now pi omega times f of j omega, well, that is just going to equal pi omega times the function f of j omega when j omega equals 0. Okay, so we know that because if you have our delta t, if it was a time domain function, for example, delta t times f of t, well, that delta t is the Dirac function, or the impulse function. It's only defined at t equals 0, and at t equals 0 it's got an area of 1. Okay, so we just use the height of 1, so delta t times f of t would just be the value of the function f of t when t equals 0. Okay, that would just be, it's just really the shifting property. So there's a function of time, and it's 0 outside here, it's 0 outside there, it's 1 at that point there, so it's just the value of 1 times whatever that function is, which is just the f of 0. Okay, so we can rewrite that as our f of 0. Now what we have here then is the function. In order to integrate the function, we divide it by 1 upon j omega. Now that's good because the previous video we did a differentiation, and the differentiation was a multiplication by j omega, which is right. So it means that when we differentiate in the frequency domain, it's equivalent to multiplying by j omega. Okay, and when we integrate, it's equivalent to dividing by j omega. But we're going to be left with this term here. Now all this term here is the equivalent of the say a DC term. So for example, if we went back to our basic integration, then if we were to say integrate a function, okay, let's say the function, function t, function 1, okay, so if we integrate that function 1, we end up with a function that looks like that. Okay, but when we've integrated it there, it could be, and it could be that function there, it could be that one, or that one, or that one. Okay, it could be any function there, say t plus a constant. Okay, because that's got gradient 1, that's got a 0 gradient. Okay, when we look at the integral there will be a function there of a gradient, and the gradient would be 1. Okay, but that's got gradient 1, that's got gradient 1, they've all got gradient 1. So whenever we do the integral, we're going to have this constant term cropping in, right, t plus c. So it's just basic calculus. Now that's what the pi delta omega f of 0 is. Okay, so in effect it would represent, in electrical engineering it would represent a DC term. Okay, so but that is what we were looking at there. Okay, now we can actually see that in MATLAB, so I'll just put it in here and I'll get it in MATLAB just now. I'll get it up here. Let's be MATLAB. MATLAB, that's us. I think I can get MATLAB up there. Okay, so if I was to, we have two functions, so that's our f of t. Okay, that's the function that I'll need to bring up here actually so I can see it as well. Okay. Okay, that's it. So that's the function there that we're going to integrate, and that's the unit step. Okay, so whenever we go through this convolution, you'll see that working just now. So if I press return there, so there you go. So you'll see this coming along. Whenever the areas overlap, this is going to increase, and it's going to generate a triangle. Okay, or a line. So there you go. The area is increasing linearly as this shifts along. When we get to that point there, now you notice this runs along, it keeps going. Now that means at that point there would actually just keep continuing. It would just keep continuing up along there forever. Okay, so what we really want to do is we want to stop it just at that point there, and if we stopped at that point there, then this would drop down to here, we would continue along at 0, and we would just have had the value of the integral. Okay, so that's all there is to this, and I'll get you in the next video. Thank you, goodbye.